Hey, what's up, chemistry people? Mr. Boylan here. Today, we are going to make qualitative or quantitative predictions about galvanic/voltaic cells based on half-cell reactions and potentials, and analyze these cells to identify properties of the underlying redox reactions. Whew, sounds super complex, but I think you'll find that the stuff that we're going to talk about is pretty easy peasy. But let's break that content objective down a little bit. First thing we're going to do is we're going to describe a galvanic/voltaic cell. Again, sort of keep in mind those two terms are interchangeable. So if you hear galvanic or you hear voltaic, talking about the same kind of electrochemical cell. Two, we're going to calculate what's called the electromotive force, or the E for the galvanic or voltaic cell, under standard conditions. And it's important to note this little knot that you see by that E cell indicates that we're under standard conditions, because there'll be some times where we're trying to figure out the electromotive force of a cell that is not under standard conditions. And then we're going to relate this quantity called delta G, or Gibbs free energy, to the electromotive force of a cell for galvanic slash voltaic cells, and then explain sort of what it means if we have positive or negative values for either one of those quantities. All right, so hopefully you had a thrilling time watching that introductory video to what's going on in voltaic cells. This quick animation here just shares with you essentially what you just watched. We're going to talk a little bit about what you see going on in this animation here, hit some of the key points, and then work through a couple of quick problems that you'll have to be able to do when you're working with galvanic slash voltaic cells. All right, so essentially, galvanic cells are just thermodynamically favored redox reactions, and that's some pretty high level vocabulary, especially since we haven't talked thermodynamics yet, but just recognize that it's a spontaneous reaction. It's something that's going to happen on its own, and just be aware that the AP graders are really looking for the use of this thermodynamically favored terminology, and so you should use that on any free response question, but recognize that it means the same thing as spontaneous, that it's a reaction that's going to happen on its own. And in a galvanic cell, the spontaneous redox reaction is going to produce electrical energy via the flow of electrons. So this is what we see essentially in batteries. These types of reactions power our lives every single day. If you're using a cell phone or a tablet or anything that's got a battery in it, you are using a galvanic cell. It's also really important to note that the two terms galvanic and voltaic are interchangeable here, so anytime you see one, recognize that it is synonymous with the other. Okay, so just some quick terminology here that hopefully you picked up on in that intro video that we just need to reinforce. One, you need to make sure that you're aware that a salt bridge allows the ions to flow. That's an important part of the galvanic cell. It completes the circuit and allows those ions to flow. Without it, your voltage will drop to zero almost instantaneously. You should be aware of the term anode. It's going to be important to sort of keep that separate in your mind from the cathode. The anode is where oxidation will occur and thus produce electrons. Again, oxidation is the loss of electrons, so we'll be producing electrons at the anode. And then the cathode is where reduction will occur. Again, reduction is the gaining of electrons, so at the cathode we'll be gaining those electrons. And then just sort of to keep these terms straight in your mind, a couple of great mnemonic devices. The first is anox. In other words, oxidation occurs at the anode. Red cat, reduction occurs at the cathode. And then lastly, fat cat. And we'll talk more about this one when we are actually drawing out the galvanic cells, but simply indicates the flow of electrons is going to go from the anode to the cathode. And that's just one of the things that you're going to have to be able to describe about galvanic cells. Okay, now there are a couple of ways to describe galvanic cells. The first is a cell diagram. It's important to know that it's not a picture. It's just a sort of nomenclature convention that we use to help us very quickly show what is being oxidized, or what the anode is and what's being reduced, or what the cathode is. And you've got an example here sort of at the bottom of your screen which shows a cell diagram. Again, anode is going to be on the left, cathode on the right, separation there indicated by double lines, which is your salt bridge. A picture of the cell is where you get to bust out your art skills. You will have to draw or be comfortable with looking at the drawings of a galvanic cell. It's going to show the oxidized and reduced species as well as the salt bridge. You have to be able to pick the flow of electrons in your picture. And keep in mind that although the cell diagram always has the anode, salt bridge, cathode, your picture may or may not be in that order. So just be on the lookout for that. It can often cause confusion if you're used to doing the cell diagram and you just always anode cathode it. So here's an example again where obviously the cathode is first on your left hand side and anode is on the right, but you'll have to be able to draw these things, and it doesn't have to be beautiful. This is obviously much higher level than you will be required to do, but you have to have all these components. So you have to be able to write in the half reactions that are occurring in each cell, which one's the anode, which one's the cathode, connect this with a salt bridge, and then indicate, of course, the flow or the direction of the electrons. And if you keep that fat cat in your mind, it's always going to go from the anode to the cathode, and we'll practice that.